payment transactions randomly timed out with no errors in the logs. The root cause? A misconfigured switch port in a different VLAN silently dropped ARP requests. Here's exactly why. Welcome to TheCodeForge. Before we dig into that production issue, let's cover the OSI model. The OSI model is a conceptual framework that standardizes the functions of a telecommunication system into 7 abstraction layers. It exists to solve a fundamental problem. Without it, engineers would have no shared language to diagnose failures or ensure interoperability. The physical layer is where data hits the wire. It defines hardware characteristics, voltage levels, cable types, and bit rates. When you plug an Ethernet cable in, you're making a layer 1 connection. If the cable is damaged, everything above it fails silently. Always check the physical link first. Use ethtool to verify link detection, speed, and duplex. Also check error counters for CRC errors. A climbing CRC count means a bad cable. The data link layer organizes raw bits into frames and adds MAC addresses. Switches operate here, forwarding frames based on MAC addresses. VLANs logically segment a switch into multiple broadcast domains. A VLAN mismatch looks exactly like a dead network. Use these commands to inspect Layer 2 connectivity. If a device's MAC address isn't in the switch table, the frame won't be forwarded. Always verify VLAN assignments when you see asymmetric connectivity. The network layer handles logical addressing with IP addresses. Routers look at the destination IP and decide the best path. This is where fragmentation happens if a packet is too large. Always check the routing table before assuming a firewall is dropping traffic. Use IP route show to see the routing table. Traceroute shows you the actual path packets take. If a packet can't find a route, it's dropped silently. Always verify with traceroute after any routing change. The transport layer decides the type of conversation. TCP ensures reliable delivery with handshakes and retransmissions. UDP is fast but unreliable. Port numbers let a single host run multiple services. Stateful firewalls track connection state. If the conntrack table overflows, new connections are dropped. Use TCP dump to capture the TCP three-way handshake. If you see SYN sent but no SYNACK, the server isn't listening or a firewall is dropping packets. SS shows all connections and their states. These 3 layers deal with end-user data. Session manages the dialogue, presentation handles encryption and compression, and application is what users interact with. Most network troubleshooting for developers stops at layer 7, but the root cause is often lower down. The article correctly notes that the OSI model is a reference framework, not an implementation. However, it's crucial to understand that the real-world internet runs on TCP/IP, which collapses OSI's 7 layers into 4: application, transport, internet, network access. When debugging, map OSI layers to TCP/IP equivalents. OSI Layer 5 session and Layer 6 presentation have no direct TCP/IP counterparts. Their functions are absorbed into the application layer. This mismatch can cause confusion if you expect to see session layer handshakes in packet captures. The article emphasizes bottom-up debugging. Here's a concrete script that automates the initial checks across layers 1-4, helping you quickly isolate the failing layer. Run this on the affected host to gather a snapshot of physical link, ARP, routing, and port reachability. The article mentions MTU issues, but doesn't highlight a common production pitfall in cloud and Kubernetes environments. Overlay networks, e.g., VXLAN, GENEV add header overhead, reducing the effective MTU for pods. If the node's MTU is 1500 and the overlay adds 50 bytes, the pod's effective MTU becomes 1450. Sending a 1500 byte packet from a pod causes fragmentation, leading to performance degradation or silent drops. Always verify pod MTU with kubectl exec pod IP link show eth0 and adjust CNI configuration accordingly. Use OpenSL client to debug TLS handshake failures. Nmap can enumerate supported ciphers. Curl with trace ASCII shows every byte sent and received, including TLS handshake details. Let's walk through a real DNS query. Your browser constructs a DNS query at layer 7. It gets wrapped in a UDP header at layer 4, an IP header at layer 3, and an Ethernet frame at layer 2 before hitting the wire. If any layer fails, the query fails. That's why bottom-up debugging works. This script walks through each layer systematically. Start at layer 1 with ethtool, then ARP, routing, port connectivity, and finally the DNS query. 9 times out of 10, you find the problem before you even look at the code. Cloud providers map the OSI model directly. Your virtual private cloud is a layer 3 construct. Subnets are layer 2 broadcast domains. Kubernetes adds an overlay network that encapsulates packets, adding header overhead. A misconfigured CNI MTU can silently fragment packets, causing performance loss. To trace a packet from a pod to the internet, start inside the pod. Check the routing table, ping an external IP, inspect the CNI interface, and check conntrack on the node. This bottom-up approach isolates the failing layer quickly. The OSI model is a reference model, not an implementation blueprint. TCP/IP is what actually runs the internet. OSI describes how networking could work. TCP/IP is how it does work. This mismatch causes confusion when debugging. Don't expect to see OSI layers in your packet captures. This Python code maps OSI layers to TCP/IP layers. Notice that OSI layers 5 and 6 have no direct TCP/IP counterpart. They're absorbed into application codecs or managed by TCP ports. Use this mapping to avoid confusion when debugging. Encapsulation is the core mechanic. Each layer wraps the data from the layer above with its own header. By the time your HTTP request hits the wire, it's been wrapped in TCP, IP, and Ethernet headers. The receiving end unwraps each layer in reverse. This is why MTU issues cause mysterious timeouts. This function simulates encapsulation. Each layer adds its own header with specific fields. Understanding this structure helps you read packet captures like a senior engineer. The OSI model is layered for one brutal reason: abstraction at scale. Without layers, every engineer would need to understand every hardware detail to troubleshoot a single timeout. Layers let you swap out the physical layer without rewriting your TCP stack. Each layer is a contract. This code simulates a layer 3 failure with 1% packet loss. The application sees a timeout, but the root cause is at layer 3. Always identify which layer actually failed before touching configs. The OSI model exists because pre-1984 networking was the Wild West. Every vendor had their own stack. The OSI model gave everyone a shared vocabulary. When an engineer says, "That's a layer 7 issue," every team member knows exactly where that responsibility ends. This class maps protocols to OSI layers: HTTP at layer 7, TCP at layer 4, IP at layer 3, Ethernet at layer 2. The framework lets you hire generalists. A dev can talk to a network engineer about encapsulation without knowing the specific hardware. This is the same issue we highlighted at the start. Here's exactly why that happened. The payment service was connected to a switch port configured for a different VLAN. ARP requests for some destinations were silently dropped by the switch's MAC filtering rules. The application saw random timeouts, but no errors in the logs because the packets were dropped at layer 2. The fix was simple: change the switch port VLAN membership to match the server's VLAN. We verified connectivity by checking the MAC address table on both ends. The fix token was switchport access VLAN 10. After that, no more silent drops. Always start debugging from the bottom of the OSI model. This is the exact configuration that caused the incident. The switch port was set to VLAN 20, but the server expected VLAN 10. All frames from the server were dropped because the switch didn't forward them to the correct VLAN. Always verify VLAN assignments when you see asymmetric connectivity. Stateful firewalls track connection state in a conntrack table. When it fills up, new connections are dropped silently. The default size of 65,536 fills fast under load. Increase it to 262,144 or more, and monitor the table size with conntrack S. In Kubernetes, overlay networks add header overhead. If your node MTU is 1500, the pod's effective MTU is 1450. Sending a 1500 byte packet causes fragmentation, which can lead to silent drops and severe throughput loss. Always set the correct MTU in your CNI config. When debugging a network issue, always start at the bottom. Check the physical link, then ARP, then routing, then port connectivity, and finally the application. This systematic approach isolates the failing layer quickly. Let's run through some common interview questions. What is the OSI model? A 7-layer framework standardizing network communication. Which layer does a VLAN mismatch affect? Layer 2, data link. How does encapsulation work? Each layer adds its header to the payload from above. And a few frequently asked questions. Why is the OSI model important? It provides a common language for troubleshooting. What is the difference between OSI and TCP/IP? OSI is a reference model. TCP/IP is the actual implementation. How do I debug a network issue? Start at layer 1 and work up systematically. The OSI model is a powerful tool for understanding and debugging network communication. Remember to always start at the bottom and work your way up. A VLAN mismatch is a classic layer 2 issue that can cause silent packet drops. Use the model to isolate failures quickly. Ready to go deeper? Up next, HTTP 1.1 vs HTTP 2 versus HTTP 3, QUIC, then WebSockets explained, then long polling versus SSE versus WebSockets. Find them all at TheCodeForge.io. Thanks for watching. The full article and code examples are covered in detail at TheCodeForge.io.